Okay, let's do a second example. Suppose we have the following data points, x1, x2, and x3, with y1, -1, and y2 and y3 are both 1. Find the maximal margin hyperplane and identify any support vectors. Our convex optimization problem takes the form minimize f of beta 0, beta 1, beta 2, where beta 0, beta lies in R3, given the constraint g sub I of beta 0, beta 1, beta 2 is less than or equal to 0 for I equals 1, 2, and 3, where f of beta 0, beta 1, beta 2 is 1/2 the norm of beta squared, and gi is given by 1 minus yi times beta 0 plus beta 1 xi1 plus beta 2 xi2 for each I equals 1, 2, and 3. So g1 is given by this. If we plug in the values for our data. Okay. And similarly, G2 is this, and G3 is this. The dual Lagrangian is given by L sub D of X alpha is this. This is the formula for the dual Lagrangian. Okay, so if we plug in the values for our data, we will get this here. Okay. Okay, we want to maximize L sub D subject to the constraints alpha I being greater than or equal to 0 for all I, and alpha 1 y1 plus alpha 2 y2 plus alpha 3 y3 equals 0. That is, we need alpha I greater than or equal to 0 for all I, and negative alpha 1 plus alpha 2 plus alpha 3 equals 0. Okay, I just plugged in the values for the y's. Now, using alpha 1 equals alpha 2 plus alpha 3, rewrite L sub D as follows. Okay, I just plugged in alpha 2 plus alpha 3 for alpha 1. Now, simplifying, we get L sub D equals to this. Okay, so it's just in terms of alpha 2 and alpha 3. So we want to maximize L sub D subject to the constraints where alpha 2 and alpha 3 are greater than or equal to 0. So we're maximizing L sub D on the positive orthant, alpha 2 greater than or equal to 0 and alpha 3 greater than or equal to 0. So it's just this quadrant here in the plane. Let's look for any critical points in the interior of the positive orthant by setting the gradient of L sub D equals to 0. Okay, the partial of L sub D with respect to alpha 2 is this. The partial of L sub D with respect to alpha 3 is this. Okay, so setting the gradient of L sub D to be 0, okay, we get this set of equations. Okay, but we get a contradiction. So this system of equations has no solution. Okay, so there is no critical point in the interior of the positive orthant, alpha 2 and alpha 3 being greater than or equal to 0. We need to check the boundaries where alpha 2 is 0 and alpha 3 is 0. Okay, so that's this line here and this line here. Okay, so the boundary of this quadrant. Okay, so on alpha sub 2 equals to 0, L sub d has a local max at alpha 3 equals to 1/10 relative to the boundary alpha 2 equals 0 and alpha 3 greater than or equal to 0. Okay, the value of L sub d at 0, 1/10 is 1/10. On alpha 3 equals to 0, L sub d has a local max at alpha 2 equals to 2/5 relative to the boundary alpha 3 equals 0 and alpha 2 greater than or equal to 0. The value of L sub d at 2/5 0 is 2/5, which is bigger than 1/10. Since every global max is a local max, the global max has to occur at a critical point relative to a portion of the boundary. Since the local max at 2/5 0 is greater than the local max at 0, 1/10, the candidate for the global max is 2/5 0. In fact, we can show that for a fixed alpha sub 3, the local max value relative to the line L sub alpha 3, given by the set of all pairs alpha 2, alpha 3, where alpha 2 is greater than or equal to 0. So the local max value relative to that line decreases as alpha 3 increases. Okay, therefore there is a global max at 2/5, 0. L sub d of alpha 2, alpha 3 has a global max at alpha 2, alpha 3 over the positive orthant if and only if L sub d of alpha 1, alpha 2, alpha 3 has a global max at alpha 1, alpha 2, alpha 3 over the set of all vectors alpha 1, alpha 2, alpha 3, where alpha 1 is alpha 2 plus alpha 3, and alpha 2 and alpha 3 are both greater than or equal to 0. So it follows that L sub d of alpha 1, alpha 2, alpha 3 has a global max at 2/5, 2/5, 0. Okay, so here we just solve for alpha 1 as 2/5. Okay, since we already know what alpha 2 and alpha 3 are. Okay, now beta is given by this. So if we plug in the values for xi and yi and alpha I, we'll get this vector here. So beta 1 is 2/5 and beta 2 is negative 4/5. By complementary slackness, alpha I times this expression is 0 for all I. Okay, so this holds for, in particular, this holds for I equals to 1. Okay, so for I equals to 1, if I plug in all the values, I get this. Solving for beta 0, I get 1. Okay, so beta 0 is 1, beta 1 is 2/5, and beta 2 is negative 4/5. Our hyperplane is given by this formula here. So plugging in the values for beta 0, beta 1, and beta 2, we get this. Okay, solve for x2, and we get this equation. Okay, now let's take a look at the graph of this line here. Okay, it's this purple line. Here's the data points, x1, x2, and x3. And our line here separates the two classes. Okay, so this is our maximal margin hyperplane. Since alpha 1 and alpha 2 are non-zero, we have that x1 and x2 satisfy this equation. Let me write that here. Okay, so x1 and x2 satisfy this equation, hence x1 and x2 lie on the margin and are therefore support vectors. Okay, you can imagine here, if we draw a line here and here, okay, forming a slab, x1 and x2 lie right on the edges.